Hello everyone, myself Prateek Mishra and I welcome you all to the YouTube platform of IMS Gate Academy. Today we are conducting this session in which we will going to discuss previous year questions asked for structural analysis for the year 23 and 22. So stay tuned till the end of this session because this session will be very beneficial for you, especially when I talk about the most important concepts of structural analysis, namely moment distribution method, influence line diagram and truss analysis, in which we are seeing regular questions asked every year. So one by one we will going to discuss all the questions asked in the year 22 and 23. I'll show you the question, give you 2 minutes of time, and then in that time if you are able to solve it, please answer it in the chat box. And one more request from all of you, please share this session to the maximum possible people. So let's start this session with a very exciting question asked in the year GATE 23. Let's see this question. So this is one of the question asked in the year GATE 23 with respect to analyze whether the structure is stable or unstable. We are given with the three structures, structure 1, structure 2 and this is my structure 3, right? And with respect to these three structures, we need to find out which of these structures are stable or which of these structures are unstable, right? 4 options are given to you. So first you analyze this, I'll give you 2 minutes of time and then we will start with the question. Solution. So this is your first question. Give it a try. These are your first 2 structures. Okay, let's see this. The first structure is our beam in which 2 internal hinges are present, one at B and the other at D. There is one guided roller support at this end E, roller support at C and hinge support at A. And we need to find out whether this beam is stable or not. My dear students, in order to check for the stability of the beam, the only criteria is check for the degree of static indeterminacy. If degree of static indeterminacy for the beam is less than 0, then we will say that the beam is an unstable structure. Okay. So let's check for the degree of static indeterminacy for this beam. Let me draw this beam in front of you first. This is your beam having hinge support at this end. Then I have a roller support. And then I have a guided roller support at this end. This is my beam. 2 internal hinges are present in between. This is 1, this is 2, right? Let me name this the A, B, C, D and E. This is A, B, C, D and E. I am writing here. For checking stability of beam, go for DS calculation. If degree of static indeterminacy is greater than 0, then we say that the beam is a stable beam. Greater than or equal to 0, then we say that the beam is a stable beam. If your degree of static indeterminacy DS is less than 0, then we say that beam is an unstable beam. So this is the only criteria for checking the stability of the beam, right? So degree of static indeterminacy for the beam DS is equal to number of unknown reactions minus equilibrium equations minus extra equations due to hybrid joint. So this is my formula for calculating the degree of static indeterminacy for the beam. Number of unknown reactions. So check on this. So this is my one support reaction, another support reaction like this, one support reaction here, and one support reaction and one moment like this. Okay. So the number of unknown reactions are how much? 1, 2, 3, 4 and 5. Number of unknown reactions are 5. Number of equilibrium equations are 3. Now you have to check over this, right? You have one hybrid joint here and one hybrid joint here, due to which the number of extra equations that we will get is 2. So this is 2, right? I think this one is also a roller support, not a guided roller support. Okay. This is a roller support. So in case of roller support, we will not get this moment, right? So here number of unknown reactions are 4. So this will be -1, right? So DS is less than 0, therefore this beam is an unstable beam. This beam an unstable beam. This is a roller support, not a guided roller support, right? Okay, so first beam is our unstable beam. This is my unstable beam. This beam is my unstable beam, right? Now next one is this frame given to us. In order to check the stability of the frame, we have to look into the position of external support reactions. If external support reactions are parallel to each other, then in that case, your structure will be unstable. Second, if your external support reactions are concurrent at a point, then in that case also your structure will be unstable. When you look into the support reactions here, you have one support reaction like this, you have another support reaction like this, you have one support reaction like this, and you have one support reaction like this, right? These are all the support reactions that are there for this structure. And when you observe closely, you will find that all these 4 support reactions are concurrent at this point. So if any moment you apply, there will be no resisting moment developed by the support reaction, hence the structure will become unstable. So since the support reactions are concurrent at a point, therefore this structure is also an unstable structure. This is also an unstable structure, right? This is also an unstable structure. So when I talk about beam, in order to check the stability, you have to check for degree of static indeterminacy. Particularly for frame, if you have to check for the stability, you have to check what is the position of support reaction. If support reactions are parallel to each other, then in that case also, you will have an unstable structure. If your support reactions are concurrent at a point, then in that case also, your structure will be unstable, right? So both of these structures are unstable. Now check on the third structure. This is the frame given to you. This is a truss basically. In order to check for the stability of the truss, again, first criteria is degree of static indeterminacy, DS. So if I talk about this frame or truss, not frame, I talk about truss. This is a pin jointed truss. This is my pin jointed truss. For this pin jointed truss, degree of static indeterminacy, DS, is M minus 2J plus R, right? Number of members, you can just count the number of members, 1, 2, 3, 4, 5, 6, 7, 8, 9. Number of members are 9. Number of joints, 1, 2, 3, 4, 5 and 6 joints. So 2 into 6. Number of support reactions are 3. 2 here, this is one support reaction and this is the another support reaction, and 1 here. So degree of static indeterminacy for this truss is equal to 0, right? This is your first criteria for checking the stability of a truss, okay? This is not the ultimate criteria, this is just the first criteria. Now if I talk about to check the stability of the truss, the arrangement of the members should make a perfect truss, okay? Now if I talk about a perfect truss, you observe this 2 blocks, right? In this first block, there is no diagonal member. So if any load you apply, this member or this block will going to distort and will create instability. On the other hand, this block is oversafe. It is diagonally supported by both the diagonal members. So due to this first block, there is no diagonal member, therefore instability exists in this block. And instability in this block will make this entire structure to be unstable, okay? So in fact, the degree of static indeterminacy for this truss is 0, is still due to the absence of the diagonal member, there is instability in this block which makes the entire structure unstable. So this truss is also an unstable structure. This is also an unstable structure. So all the 3 structures are unstable structures. So when you check for options, your option number D is all 3 structures are unstable. Option A is structure 1 is unstable, structure 2 is unstable and structure 3 is unstable. So A, B, C are your correct options, right? So this is how you need to check for the stability of the structure. So if I just summarize this entire thing, I will write for checking stability first one for beams, check using DS. If DS is less than 0, then your structure is an unstable structure. Okay. Second, for pin jointed structure, Now your pin jointed structure may include trusses, okay, mainly trusses. For pin jointed structure, first one is check DS. Again, if DS is less than 0, then your structure is unstable. The second check is check for formation of perfect truss. Means every block should be connected with a diagonal member. If this is my one block of the truss, then it should be connected with a diagonal member either like this or like this. And if you want to make it over safe, you can also connect with both of the diagonal members. So that is not a problem, right? So this is your criteria for checking the instability. The third criteria for checking the instability is check for support reactions. If support reactions are parallel like this, right? It can be parallel vertically or horizontally, then it makes the structure unstable. If your support reactions are concurrent at a point like this, then also your structure is unstable. Structure. So right now in the board, all the details are given to you with respect to check the stability or instability of the structure, right? So you can just follow these 2-3 points in order to check for the stability. I hope you have understood the solution. Let's move on to the next question. Okay, this is again a question asked in gate 23. From truss analysis, try to solve it. I am giving you 2 minutes of time. Go for it. Okay, let's see this question. So this is the question asked for the deflection of truss joint, right? And this is the question framed from the unit load method. Question says that consider the pin jointed truss shown in the figure, not to the scale, all members have the same axial rigidity AE. Members QR, RS, ST have the same length L. This is member QR, RS and ST have the same length L, right? Angles QBT, RCT, SDT are all 90 degrees. These are all 90-degree angles, right? This one. Then you have angles BQT, CRT, DST are all 30 degrees. All these angles are 30 degrees, okay? The joint T carries a vertical load P. The vertical deflection of joint T is KPL by AE. Then you need to find out the value of K. So this is one of the very simple questions framed from the unit load method. Now first of all, my dear students, understand what is a unit load method. For example, this is the truss I am considering, right? And this is not the truss that is given to you. I am just explaining you what does unit load method tells us. If a load is applied like this at this joint A, this is A, B, C, right? And I have to calculate the horizontal deflection of this joint A. So what unit load method tells us is, first calculate all the member forces due to this external load P. So that value of forces will be termed as P values. What are P values? P values are forces in member due to external load. Okay. So P values are forces in all these members due to external load. Now step number 2 in unit load method is, I want horizontal deflection of this point A. So what I will do is, I will remove all the external load and I will apply a horizontal unit load at point A. So if this is my frame again, this is my truss again, like this, right? This is point A. So I'll remove all the external load and I'll apply a unit load in horizontal direction because I want horizontal deflection of point A. And then I'll calculate again all the member forces. And now the member forces will be termed as K values. The member forces will be termed as K values, right? What are K values? K values are forces in members due to unit load applied in the direction of desired deflection. So what are K values? K values are the member forces due to unit load applied in the direction of desired deflection. I want horizontal deflection at A, that's why I have applied a unit load in the horizontal direction. Then the horizontal displacement of this point A is, so I'll write here itself, the horizontal deflection delta horizontal of point A is summation of P values into K values into length of every member divided by axial rigidity for every member. For example, say the P value here is P1 and K value here is K1, length of the member is L1 and axial rigidity is A1 E1, okay. Like that, I will take the summation of P1 into K1 into L1 divided by A1 E1 and I will take that for all the members. So like this, if I have to calculate the total deformation, this will be equal to P1 K1 L1 divided by A1 E1. This is my one term. Then for this second member, it will be P2, K2, L2 divided by A2 into E2. Then for this third member, it will be P3, L3, K3 divided by A3 into E3. So such a simple method to calculate the any kind of deflection for a truss joint. Okay. So same method we will apply to solve this question as well. We need to find out the value of K because this is the vertical deflection of joint T given to us. So first, due to this external load P, I will calculate all the member forces for this truss. Then I'll remove this load P, apply the unit load at P and calculate again all the member forces of the truss. Then I'll calculate length for every member and axial rigidity is given same for every member. So simply I have to take the summation of that. So let's start this. So I have a truss like this. Let me first draw the truss properly. This is my truss. This is roller support at B and hinge support at Q. So you have B, C, D, T. This is B, C, D, T. And then I have S, R, Q. This is S, this is R, and this is Q. You have one external load P acting here, right? So I have to calculate all the member forces first. This angle is given as 60 degrees. Okay. Now, every time when you get a question, especially from the truss in your examination, the first thing is check for zero force member. That will going to reduce your calculation like anything, right? So I'll start with this. When you look at this joint D, so this DS is not in line with the member CD and DT. Therefore, this is a zero force member. This is my zero force member. Then at joint S, forget this member. You look into this member SC. This member SC is not in line with the other two member. Therefore, this is also a zero force member. Then at joint C, when you look into this member CR, this is not in line with BC and CD. Therefore, this is also a zero force member. When you look into joint R, this member RB is not in line with the other two members. Therefore, all this is also a zero force member. Next, when you look into this joint B, at this joint B, the support reaction is in line with the member BC. So this is your third member which is not in line with the support reaction and the member force. So force in this member is also zero force, right? And when I was drawing all these zero force member, one thing is common, that there is no external load acting at all the joints. If external load would have been acting, then we cannot say possibly whether the forces in the member is zero force or not. So right now this is the situation and these are all the zero force member. Now only we have to determine member force dt and member force st, because this member force dt will be equal to member force cd will be equal to member force bc. Similarly, member force st will be equal to member force rs will be equal to member force qr, because all these members are in line. Remember, whenever the members are in line, the member forces are equal. So for calculating this member force dt and ts, I will take joint T. So consider joint T. So I'll assume that the force in this member is compressive in nature, like this, and force in this member is tensile in nature, like this. Okay. So if I just draw this joint T, this is my joint T over which one external load P is acting, and then I have this member force. This is F TS and this is F. This is TD, right? And this angle is 60 degrees. Now just consider the equilibrium of this joint T. So take the summation of vertical forces equal to 0. From there you will get force in the member TS. So this is joint T, right? Take summation of vertical forces equal to 0. So F TS sine 60 degrees should be equal to P. Now sine 60 degree is root 3 by 2. So FTS is equal to 2P by root 3. This is my first member force, right? Now second one. For calculating member force TD, you take summation of horizontal forces equal to 0. So you have two horizontal force, first FTD and another one is the component of FTS, right? So next is take summation of horizontal force equal to 0. So FTD acting rightwards, so I'll take this as positive. Then FTS cos 60 acting leftwards, so I'll take this as negative. FTS cos 60 degrees. And this should be equal to 0. So FTD I have to calculate, FTS I have already calculated, multiplied by the cos 60 will give me the value of FTD. So FTD is equal to, FTS is 2P by root 3 into 1 by 2, cos 60 is 1 by 2. So FTD comes out to be 1 by root 3. Okay, so we have determined force in the member TD and force in the member TS. Now first we consider this line. Member TS, SR and SNRQ are in line, so the member forces will be equal in nature. So from here I can write force in the member TS is equal to force in the member RS is equal to force in the member RQ. Similarly, I can write force in the member TD is equal to force in the member CD is equal to force in the member BC. The nature of all these forces will also be same. This force is compressive in nature and this force in the member TS is tensile in nature. So I will write like this. Force in the member TS is equal to force in the member SR is equal to force in the member RQ is equal to 2P by root 3, and all these forces are tensile in nature. Okay. Next, force in the member TD is equal to force in the member DC is equal to force in the member CB is equal to P by root 3, and all these forces are compressive in nature. And all these forces are compressive in nature, right? So just by observing this, that first thing that we did is identifying the zero force member. That has reduced our calculation drastically. That's why the question framed from unit load method always contains zero force member. So whenever you see any question from the deflection of truss, the first step is check for the zero force member. That will going to reduce your calculation very drastically. Now step number 2, so these are all my P values. That is the member forces due to the external load P. All these are my P values. All these are my P values, right? Now one more thing I need to calculate here, that is what is the length of the member. So in the question it is given that length of the member QR is L, RS is L, and ST is L. So length of members QR, RS and ST, all these length are given to us as L. We have to determine length of these members, okay, because these members are zero force members, so we need not to worry about these. So for determining this length, you can consider this triangle SDT. So cos 60 is equal to this base into hypotenuse. So when you take cos 60 degrees, this is equal to this base dt by hypotenuse, which is L. Cos 60 is 1 by 2, so dt will be L by 2. So this length will be L by 2, this length will also be L by 2, and this length will also be L by 2. So the length for the member dt, dc and cb, this is equal to L by 2. Okay. Now next step is calculation of the K values. For K values, you have to remove all the external load and you have to apply the unit load in the desired direction of deformation or deflection. We want the vertical deflection at point T, so we will remove all the loads and we will apply a unit vertical load at the point T. So again, let me just draw this. So this is my point T, this is T, this is S, this is R, this one is Q, this is D, this is C, this is B. This angle is 60 degrees. Okay. So I'll apply a unit load at T, and that is a vertical unit load, right? Because I want the vertical deflection of this joint T. So again, consider this joint T and take the summation of horizontal and vertical forces. So considering joint T, This is my unit load. And force in the member TD is denoted by K TD. And here I'll assume the direction like this. This is K TS. Okay. This angle is 60 degrees. Now these are the member forces due to the unit load at point T, right? Before that, just go with the zero force members. So we have already identified these are all my zero force members. Since type of loading condition is same, only the magnitude of load has changed. So zero force members condition is also same. So first step is take the summation of vertical forces equal to 0. So you have KTS sine 60 degrees. This should be equal to 1. Okay. KTS sine 60 degree should be balanced by this unit load 1. So KTS comes out to be, this will be root 3 by 2. So 2 by root 3. This is KTS. And the nature of KTS is again tensile. Next is take summation of horizontal forces equal to 0. So you have KTD minus KTS cos 60 degrees equal to 0. So cos 60 is 1 by 2 and KTS is 2 by root 3. So this term will be, this entire term will be 1 by root 3. So KTD will be 1 by root 3. Okay. KTS will be tensile in nature and KTD will be compressive in nature. Okay. Again, if you check this collinear members, so member forces in member KTS is equal to force in the member SR will be equal to force in the member RQ, and that will be 2 by root 3. Similarly, force in the member TD will be equal to force in the member DC will be equal to force in the member CB, and this will be equal to 1 by root 3, and this will be compressive in nature. So I'll just write down this K value is 1 by root 3, this is also 1 by root 3, and this is also 1 by root 3. The nature of the forces is compressive. These are the K values of compressive nature. Then the member forces in member TS is 2 by root 3, and this is tensile. This is equal to force in the member SR will be equal to 2 by root 3, again tensile, and this is also tensile in nature. Okay, 1 second. This is tensile in nature. This is 2 by root 3 and this is also 2 by root 3. Okay. So we have calculated all the P values, all the K values. Now the only thing we need to do is take the summation of PKL by AE. So I'll draw a table. So first I'll write members, then P values, then K values, then length, then P values, K values, length divided by axial rigidity AE. Since axial rigidity AE is same for all the members, so we need not to worry about AE, right? First of all, I'll start with member ST. Okay, TS. P value is 2 by root 3. P value is 2P by root 3. K value is 2 by root 3. Length is L. So when you take the summation, it will be how much? 4P by 3. 4PL by 3EI. Root 3 into root 3 will be 3. 2 and 2 will be 4. So 4PL by 3 AE. Sorry, not EI, AE. Next is your member SR. Again 2P by root 3. Then 2 by root 3. Length is L. Summation will be 4PL by 3 AE. Next one is your RQ. Again 2p by root 3, 2 by root 3 L, and again this will be 4PL by 3AE. Okay. Next is your member. Okay. TS, SR and RQ. Okay. Now I'll take TD. For member TD, P value is minus P by root 3. It is compressive in nature. K value is minus 1 by root 3. Again compressive in nature. Length of the member is L by 2. Okay. So when you just multiply all of them, you will come up with PL by 6 AE. This will be PL by 6 AE. Similarly, you can write down for DC. This will be minus P by root 3. This will be minus 1 by root 3. And length is L by 2. So this will also be PL by 6 AE. Then I'll write for CB. Again minus P by root 3. Then you have minus 1 by root 3. Then you have L by 2. And then you have PL by 6 AE. You have to just take the summation of all this and you will get the vertical deflection of joint T. So take summation of this. How much it will be? So this is 12 PL by 3 AE and this is PL by 2 AE. So I'll just write down. This is 12 PL, 12, or I will write it like this. This is 12 by 3. So 4 PL by AE. 4 PL by AE. And this is how much? So this is 3 PL by 6 AE can be written as PL by 2 AE. PL by 2 AE. So when you add these two terms, it will be 4.5 PL by AE. So this will be 4.5 PL by AE. Okay. So this is your vertical deflection of joint T. So I'll write here vertical deflection of joint T is equal to 4.5 PL by AE. Now in the question, you are given with the vertical deflection of joint T. And the vertical deflection of joint T is given as KPL by AE, and you are asked to calculate the value of K. So just now we have calculated the vertical deflection of joint T is 4.5 PL by AE. And in the question it is given as K, small k, PL by AE. So when you compare these two expressions, you can clearly identify that the value of K is 4.5. So for this question, your option number B is the correct option. Okay. For solving this question, it may take a bit of time, but these type of questions are very easy to solve, right? So I hope you have understood the solution. Let's move on to the next question. So this is the question. It's a very easy question. You can just take 1 minute of time and solve this. Please solve this. Okay, it's a very easy question asked this year in GATE examination for structural analysis. This is GATE 23. Question says that the Muller-Breslau principle is used to analyze the structure for. So my dear students, first of all, Muller-Breslau principle is used to draw the influence line diagram with respect to the various force responses. The forces can be like support reactions, it can be shear force, it can be bending moment. So with respect to different force responses, Muller-Breslau principle is used to draw the influence line diagram, right? So for drawing the influence line diagram for any force response, your Muller-Breslau principle is used. So for this question, your option number A is the correct option, right? I hope you have easily identified the correct option for this question. Let's move on to the another question. This is a very good question asked this year for GATE 23. I am giving you 2 minutes of time, analyze this and tell me the answer. Keep commenting in the chat box. Whatever answer you are getting, this is a numerical answer type question, so keep commenting in the chat box. Do it. This is the question asked from the various parameters that we do for moment distribution method, or from the very basics of moment distribution method. Just do it. Keep commenting your answer in the chat box. It's a very good question asked this year for GATE 23. Let's see this. The question says that for the frame shown in the figure not to the scale, all members AB, BC, CD, GB and CH have the same length and flexural rigidity EI. The joints at B and C are rigid joints and the support A and D are fixed support. Beam GB and CH carry uniformly distributed load of W per unit length. The magnitude of the moment reaction at A is WL square by K. Then what is the value of this K? Okay. So you need to identify this support reaction at A, and using this support reaction you have to compare this expression and then find the value of K. Okay. So it's a very easy question. The only few key points you should analyze for solving this. Let's see this question. So this is the beam, this is the frame given to us. this is A, B, this is C, D, and then you have G and H. This is G and this one is H. The length of all the members is L. This is L, 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 everywhere it is L, right? You need to find out the support moment or the reaction moment at A. And then you need to compare with the given expression and find the value of K. When you observe this frame, first of all, it's a symmetrical frame. Due to this symmetry, the slope at the midpoint will be equal to 0. So there is an axis of symmetry for this frame, and at the center of this beam, the slope will be equal to 0, but there will be some moment. Okay. So if I just consider the axis of symmetry like this, if this is my axis of symmetry, so at this point, say this point is O, at this point the slope of the frame should be equal to 0, but there will be some moment. So if I only consider half of the frame like this, if I only consider half of the frame like this, then this end can be replaced by a guided roller support. Reason is, the guided roller support will provide the support reaction or the support moment, and also the slope of the beam at this point will be equal to 0. So this entire frame is reduced like this. This is point A, this is B, this is G, and this is point O. Now length of this member is L by 2, length of this member is L, and length of this member is L, right? When you observe this joint B, this overhang will going to give some moment about point B, and that will be equal to W L square by 2. This is W. So moment due to this overhang at joint B is W L square by 2. So if this is my final condition, at B, due to this overhang, I have a moment like this, which is equal to minus WL square by 2. Because it's a anti-clockwise moment, that's why I am keeping the minus sign. Now, this is my joint A. Okay. This is my support reaction A, this is B, and this is O. Now, this question reduces to, if this total moment acting over the joint B is minus WL square by 2, then how much moment will come over the portion BA? The moment that will come over the portion BA, that is MBA, the moment that will come over the portion MBA, the half of the moment will be carry over to this joint A. The half of this moment will be carried over to this joint A. So now my entire discussion will be how to calculate this moment MBA. For calculating this moment MBA, first I need to calculate the distribution factor, and using the distribution factor I can very easily calculate the moment MBA. So observe this, this is my joint B. So joint is B, then members. So joint is B, member is BO and BA. Next one is stiffness K. Is stiffness K of the member, right? When you look into this member BO, right, the stiffness, since the far end is a guided roller support, so stiffness of this member BO is equal to EI by length of this member. Length of the member is L by 2. So stiffness for this member BO will be equal to EI by L by 2. This is the stiffness of this member BO. When you look into this member BA, the far end is fixed. Therefore, stiffness of this member BA will be 4 EI by length of the member. So it is 4 EI by L. This is your stiffness for member BO and BO meeting at the joint B. The next step is calculating stiffness of joint. So stiffness of joint is simply the sum of stiffness of all the members meeting at the joint. So this is equal to 2 EI by L plus 4 EI by L. So when you calculate this, you can easily identify that this is 6 EI by L. So I'll just write down directly. So stiffness of the joint is 6 EI by L. Next is calculation of distribution factor. So distribution factor is, for member BO, distribution factor is stiffness of the member BO divided by the stiffness of the joint. So when you take the ratio, you will come out to be 1 by 3. Similarly, distribution factor for this member BA is equal to stiffness of the member divided by the stiffness of the joint. So distribution factor for member BA comes out to be 2 by 3. Now the total moment over the joint, which is minus WL square by 2, will be distributed in the members with respect to the distribution factors. Means 2/3 of the total moment coming over joint B will be taken by member BA and 1/3 of that moment will be taken by member BO. So therefore, moment MBA is 2/3 of total moment over the joint B, which is minus WL square by 2. So this comes out to be minus WL square by 3. This is your moment MBA. Now when you observe this, this is your fixed joint. So half of this moment MBA will be carried over to this joint A. Half of MBA will be carried over to joint A. Okay. So moment at support A is equal to half of minus WL square by 3. So moment at A comes out to be minus WL square by 6. This is your actual moment at A, minus WL square by 6. Okay. Now in the question it is given that you have to first of all compare the magnitude. So don't worry about the plus or minus sign. Moment at A is WL square by K. So moment at A in the question is given as WL square by K. And we have calculated this as WL square by 6. So from here you can clearly identify that the value of K is 6. The value of K is 6. So this is my final answer, right? The value of K comes out to be 6. So this is one of the simple question framed from the basics of moment distribution method. My dear students, moving ahead, I have to make some very important announcements, and that is, we at IMS GATE Academy conduct 3 types of classroom program. We have offline classroom program where 750 hours of teaching content will be provided to you along with theory books and exercise books. Second, we have the online classroom program where we provide again 750 hours of teaching content completely in the online mode. Third, we have the hybrid program where we have the fusion of online and offline classes conducted in Bangalore and in Vijayawada. Along with that, we provide you with My Plan sessions. These are one-to-one mentoring sessions that keeps you motivated throughout your GATE journey. So IMS GATE Academy is keeping or playing a key role in generating ranks over the years. So join us for your GATE 25 or GATE 24 courses. We are also conducting test series. The link of the test series is given in the description box. So you can check the description box and apply to our test series to have a very fruitful analysis for your all the learned concepts. Okay. Let's move ahead. let's see this question. This is the question asked in the year GATE 2022 for structural analysis. Just go for this. Again, at this time I'll give you just 1 minute of time because this is a very easy question. Go for it. Okay, time's up. Let's see this question. This is a very easy question framed from the influence line diagram and the moving loads. Question says that consider a simply supported beam PQ as shown in the figure. A truck having 100 kilonewton on the front axle and 200 kilonewton on the rear axle moves from left to right. The spacing between the axle is 3 meters. So if you consider a truck like this is your front axle and this one is your rear axle, okay, and this truck is moving like this. The front axle carries a load of 100 kilonewton and rear axle carries a load of 200 kilonewton. The spacing between these loads is 3 meters. This spacing is 3 meters, right? You need to find out the maximum bending moment at point R, and this point R is 1 meter from support P and 4 meters from support Q. So whenever such type of questions are asked with respect to the moving load, step number 1 is whichever force you need to maximize. Right now we have to find the maximum bending moment at point R. Step 1 is draw the draw the influence line diagram at point R. Influence line diagram for bending moment at R. So I'll start like this. This is my beam. This is P. This is R. And this is Q. Okay. So if I have to draw the influence line diagram for bending moment at R. So I'll draw it using the Muller-Breslow principle. What it says that, first of all, imagine an internal hinge at this point R. And then you give the unit rotation at this point R. Means the angle between the member PR and RQ should be unit rotation. So this is my unit rotation. This is member PR and now this is my member RQ. This is my unit rotation between member PR and RQ, right? So this deflected shape of the beam will going to give me the influence line diagram for bending moment at R. First step is calculate the ordinate of this point. So ordinate of this point is equal to AB by L. So A is 1 meter, B is 4 meters and total length is 5 meters. So ordinate of this point will be 1 into 4 divided by 5. So this will come out to be 4 by 5. So ordinate of this point is 4 by 5 or 0.8. Okay. Now for checking the maximum bending moment, you have to place the loads and check for the different possibilities, and then you can calculate the maximum bending moment. So first possibility is, so I am writing here, possibility 1 is front axle load is at R. The front axle load is at R. So again, I'll draw the influence line diagram. This is my influence line diagram. This is P. This is R. This is Q. This is 1 meter and this is 4 meters. And this one is 4 by 5, or you can take it as 0.8. Right? Now first possibility is my front axle load is at point R, like this. So my rear axle load will be out of the beam because the length between two axles is 3 meters and here only 1 meter is there. So rear axle will be out of the beam. So this is 3 meter. So in this possibility, the bending moment at R is equal to, when this is the possibility, bending moment at R for possibility 1 is equal to load 100 kilonewton multiplied by the ordinate of this ILD for bending moment at R. This is ILD for bending moment at R, and this is equal to 0.8. How much is this? So this is like 80 kilonewton. Okay. So just keeping this rear axle load at R, the bending moment that we are getting is 80 kilonewton. Now second possibility is keep your rear axle at this point R. Right now we have kept the front axle. Then you keep the rear axle at point R and check for the maximum bending moment. So possibility 2 is keeping rear axle at R. So again, I'll draw the ILD. This is my ILD. This is 1 meter and this is 4 meters. This is P, this is R, and this is Q. And this is 0.8. Now second possibility is keep the rear axle at R. So this is 200 kilonewton. This is the front axle. This is 100 kilonewton. Now when you keep it like this front axle will also contribute in some of the bending moment, right? For that, we need to identify the ordinate of ILD at this point. So this is 3 meters. So this total is 4. So this will be 1 meter. So we need to determine this ordinate. For determining this ordinate, we can go with the similar triangles, right? So you just take the ratio of 0.8 by this 4 should be equal to this some x value divided by 1. So when you consider the similar triangles, this is 0.8 by 4 should be equal to x by 1. So from here the value of x comes out to be 0.2. So this is your ordinate below this rear axle load, front axle load in the ILD for bending moment at R. So bending moment at R for second possibility is equal to 200 into 0.8 plus 100 into x, and x is 0.2. So this is 100 into 0.2. Calculate this and tell me. So 200 into 0.8 will be 160 and that is 20. So this will come out to be 180 kilonewton meter. So this is your bending moment at R when you have placed the rear axle at R, right? So in both of the possibilities, you can clearly identify where you will get the maximum bending moment. You are getting the maximum bending moment when your rear axle is placed at R. And the value of maximum bending moment is 180 kilonewton meter. So maximum bending moment at R, so maximum bending moment at R is obtained when rear axle is at R and BM max at R is equal to 180 kilonewton meter. This is the value of your maximum bending moment at R, which is 180 kilonewton meter, right? So this is again a question asked from the influence line diagram directly. I hope you have understood this. Chalo, let's move on to the next question. This is again a question asked from the plane truss in the year GATE 2022. So try this question. Again, I'll give you 1 minute of time. You can just try this one. Say 2 minutes. Take 2 minutes. Try this one and keep posting your answers in the chat box. Okay. So this is the question asked in the year GATE 2022 for structural analysis from truss frames. Question says that a plain truss shown in the figure is subjected to external load P and the value of P is given as 70 kilonewton. A and B are the dimensions of different members. So A is 2 meters, B is 3 meters, right? You need to find out magnitude, absolute value of force in the member EF. This is your member EF and you need to find out the magnitude of force in the member EF. That force can be compressive or tensile, that is a separate story. We only need to find out the magnitude of force in the member EF. Now, in order to solve this question, there are like two methods. First one is, you calculate the support reaction and then you start solving every joint, and that is a longer way. The second method is method of sections, and every time you get a question like this, where you need to calculate force in some of the intermediate member, you go with method of sections, right? So first, I'll calculate the support reactions. So I'll take moment about point J to be equal to 0. I'll write, so step 1 is calculation of support reaction. So what I will do, I'll take summation of moment about point J should be equal to 0, right? When you observe this point J, right, the first moment will be due to this load, and this load will give an anti-clockwise moment. The value of that moment will be P into 2A. A is 2 meters. So I will write minus P into 2A. After that, I'll substitute the values. The next moment will be due to this horizontal reaction at A. This is my horizontal reaction at A, say this is HA. And the value of that moment will be HA into lever arm is 2A minus B. I want the lever arm, right? This is the lever arm. This is the lever arm for HA, and this is equal to 2A minus B. So moment due to HA is again anti-clockwise, and that moment about J is HA into, so minus HA into 2A minus B. The next you have a clockwise moment due to VA. This is your vertical reaction at A. So VA is equal to, or the moment due to VA is equal to VA into 1, 2, 3, 4, 4A. So this is equal to plus VA into 4A, and this should be equal to 0. Now substitute all the values. So P is 70. So minus 70 into 4. 2 is, sorry, this A is 2 meters. So 2 into 2 is 4. Minus HA. A is 4. 4 minus 3 is 1. So this is 1. Plus VA into 8. This should be equal to 0. So from here I have one expression which says 8 VA minus HA should be equal to 280. This is my first expression. Okay. This is the first expression I'll got. I'll just name it as equation number 1. Now you consider this truss, and what you will do is, you take one section like this. This is my section 1-1, and I am considering only the left side of the section. When you cut this section, you have one member force. This is my member force. This is my member force. This is FE, force in the member FE. And then you have this one member force. This is FEG, right? So I am considering left side of section 1-1. Considering left side of section 1-1. I am considering the left side of section 1-1, right? First, what I'll do is, I'll write down moment about point E to be equal to 0. I am considering only left side of this truss. So when you take moment about E, there will be two moments. First due to this HA, and second one due to this VA only, because I am only considering the left side of this portion. So I'll write summation of moment about E should be equal to 0. So from here I will have the clockwise moment due to VA. So VA into 2A minus anti-clockwise moment due to HA. So HA into 2A, and this should be equal to 0. From here you can clearly identify that this is my VA. VA, A and A will be 2A. So if I have to write moment about E, so this is VA into 2A. If I have to write moment about E due to HA, it will be HA into 2A, right? So from here I'll have one relation, that is VA is equal to HA. Now substitute this relation in this equation and get me the value of VA. So I can write, so this is my equation 2. From 1 and 2, I can write 8 VA minus VA. This is equal to 280. So VA comes out to be 40 kilonewton. VA comes out to be 40 kilonewton, right? VA is 40. VA I have calculated this as 40 and it is an upward acting support reaction. Now again consider the left side and take summation of vertical forces. So when you take the left side of this section, the vertical forces acting are VA, P and EF, this. F, EF, force in the member EF. These are the three vertical forces acting on the left side. So I'll take summation of forces or vertical forces should be equal to 0 on left side for section 1-1. So I have VA acting upwards, then I have P acting downwards, then I have EF acting downwards, and this should be equal to 0. So VA we have just now calculated 40 minus P, which is 70, minus EF. This should be equal to 0. So from here the value of EF comes out to be minus 30 kilonewton. This minus sign indicates that whatever direction I have chosen for force EF, I have to just reverse that direction. But the magnitude of the force is equal to 30 kilonewton. The magnitude of force in the member EF is 30 kilonewton. So magnitude of force in member EF is 30 kilonewton. So 30 is my final answer, right? This 30 is my final answer. So this is one of the very simple question which was asked in the year GATE 2022 for structural analysis. Okay, I hope you have understood this solution. So for this question, it's a numerical answer type question. So the value of force in the member EF, this is equal to 30 kilonewton. So you have to just substitute the answer as 30. Chalo, moving ahead with the next question. So this is the question which is asked in the year GATE 2022 for structural analysis. Just go for this. I'll give you a timer for 2 minutes. Just go for this. This is again a question which was framed from moment distribution method, where the basics of moment distribution methods are used to calculate the required things. Let's see this question. This is the question asked in the year GATE 2022 for structural analysis. Question says that consider the linearly elastic plane frame shown in the figure. Member HF, FK and FG are welded together at joint F. Joints K, G and H are fixed supports. The counterclockwise moment M is applied at joint F. Consider flexural rigidity EI is equals to 10 raised to power 5 kilonewton per meter square for each member and neglect axial deformations. If the absolute value of the support moment at H is 10 kilonewton per meter, the magnitude absolute value of the applied moment M to maintain the static equilibrium is. So basically you need to find out this moment value M. Now my dear student, observe this very carefully. This moment M is applied over this joint F, right? Now some part of this moment M will be taken by this member and this member, okay? Say the moment taken by this member is say some M1. Moment taken by this member is M1. Then half of this moment will be carried over to joint H or support H. Half of this moment will be carried over to this support H. Similarly, moment taken by this member Fk is some M2. And half of this moment will be carried over to this support K. So here it will be M2 by K. Again, some moment will be taken by this member Fg. Half of this moment taken by this member Fg will be carried over to this support G. Okay. And we know that this M1 plus M2 plus M3 is equal to the total moment at the joint F, which is equal to M, right? Now, how to calculate this M1, M2 and M3? The only way to calculate M1, M2 and M3 is calculate the distribution factor for these members, and based on the distribution factor, this total moment will be distributed over this joint. So let's do this. First of all, length of this member HF is 5 meters. Length of this member will be how much? This is 3 meter and this is 4 meter. So when you apply the Pythagoras theorem, this member length will also be 5 meters. Similarly, length of this member will also be 5 meters because this is 3 meter and this is 4 meter. So this length will be 5 meter. Flexural rigidity is EI, which is same for all the three members. So I'll take this joint F. So I'll take joint F. So joint is F. Three members are meeting at this joint F. Members are FH, FK and FG. FH, FK and FG. These are the three members meeting at this joint F. Next, is stiffness of these members. The stiffness is K. So when you look into this member FH, the far end is fixed. So stiffness of this member will be 4 EI by length of the member. So it will be 4 EI by 5. For member FK, this is your member FK. The far end is again fixed. So your stiffness will be 4 EI divided by length of the member, which is again 5. So this is also 4 EI by 5. When you look into the member FG, again the far end is fixed. So stiffness will be 4 EI by length of the member. So length is 5 meters. So this is again 4 EI by 5. Next is calculate stiffness of joint. So stiffness of joint is simply the sum of the stiffness of all the members meeting at the joint. So this will be 4 EI by 5 plus 4 EI by 5 plus 4 EI by 5. So this will be 12 EI by 5. Next, you calculate the distribution factor. So for member FH, the distribution factor will be stiffness of the member divided by the stiffness of joint. So this distribution factor will be 1 by 3. Similarly, for other two members, it will also be 1 by 3, like this. So distribution factor is always the stiffness of the member divided by the stiffness of the joint, right? So distribution factor is 1 by 3. So if total moment M is acting at joint F, then moment in the member, okay, first of all, which moment I am given with? So I know the support moment at H, okay, this support moment at H, and this is given as 10 kilonewton meter. This moment is given as 10 kilonewton meter. This is 10 kilonewton meter, right? So I bother only about this moment in the member FH. So moment in the member FH, will be equal to distribution factor multiplied by the total moment at the joint M, right? So this is your moment in the member FH. Now half of this moment will be carried over to the support H. Half of moment FH will be carried over to support H. So I can say half of moment FH will be equal to moment at H, which is given as 10. This moment FH we have just now calculated. This will be total moment divided by 3, and this should be equal to 10. From here, the total moment M comes out to be 60 kilonewton meter. And this was asked in the question. The magnitude of the total moment. So the magnitude of the total moment that is asked in the question is 60 kilonewton meter. This is my final answer, 60 kilonewton meter. So the absolute magnitude of the total moment M is 60 kilonewton meter. This is my final answer, right? Chalo, moving on to our very next question. So this is the question. This is one of the last question that was there for GATE 2022. Just try this. So in the question it is given that consider a beam PQ fixed at P and hinged at Q and subjected to a load F as shown in the figure. The static and kinematic indeterminacy for the beam is. So here is a beam given to you in which an inclined load is applied. You need to calculate the static and kinematic indeterminacy. So that's a very, very easy question. So static indeterminacy is number of unknown reactions, minus number of equilibrium equations. Since no hybrid joint is there, so we will not consider the effect of those hybrid joints. So number of unknown reactions are how much? This is 1. This is the fixed support. So 3 number of unknown reaction. Vertical, horizontal and moment. This is the hinge support. So 2 unknown reactions. So total number of unknown reactions are 5. Then number of equilibrium equations are 3. So degree of static indeterminacy ds for this beam comes out to be 2. This is your degree of static indeterminacy, which is 2, right? Now talking about degree of freedom or degree of kinematic indeterminacy dk for the beam. So this is equal to 3j minus r. At every joint, there is 3 degrees of freedom, but these degrees of freedom are restricted by these support reactions. So we have 2 joints, so 3 into 2 minus support reaction, which is 5. So degree of kinematic indeterminacy or degree of freedom comes out to be 1. So just check with the option. Degree of static indeterminacy is 2 and degree of kinematic indeterminacy is 1. So your option number A is your correct option. So these are all the questions, my dear students, which are asked in the year GATE 23 and GATE 22 for structural analysis. I hope you have learnt many new and simple things about structural analysis. Especially this year, the questions are more oriented towards the basics, and the same we are expecting for GATE 24. So I hope you have learnt many new things. I hope you have enjoyed the session. Tomorrow we will going to come up with question of the year 21 and 20 asked for structural analysis. So join me at same time 5 p.m. at the same YouTube platform of IMS GATE Academy. For today, myself Prateek Mishra signing off with a smile, and I wish you all the best for the upcoming GATE examination. Thank you so much for listening patiently. Have a very good night ahead.